And so I think you're all aware that we did a swap with Ivan Velenik with the other course. So last week you had 4 hours of statistical mechanics, and this week we will meet today and also on Thursday. So we'll have 4 hours of this course. Let me just review what we were doing 2 weeks ago. So if you recall, we are trying to analyze the eigenvalue density very precisely of GUE. And I think the notation I used was rho. Yes, so if you recall for GUE, so this is just review. So for GUE, the eigenvalue density was the following quantity. It was given by a product of Gaussians. So I had some normalization constant. I don't usually care much about these numbers. They're just some positive numbers chosen so that this thing is a probability density. And then I had e to the minus sum over these. I had a product of these Gaussians, and then I had a Vandermonde determinant. So in fact, for the GUE in the original normalization, I have an n, and then I had a product of I less than j, lambda I minus lambda j squared. Okay, so that was the density for GUE. Now we do a change of variables. Which is the following. This one can of course do, and this I do mainly so as to get rid of this n here, and then the density becomes it's the same thing except this n just vanishes. So the goal is to analyze this density, and the key observation was one we made last time. So there were 2 important observations. The first one was that this is the Vandermonde determinant. In fact, it's not like that. This is the square. So from last time we had proposition 38, which told us that let me write it this way, round xj minus xi, product I less than j. This thing is equal to this Vandermonde determinant, so it's I and j go from 1 to n. Okay, so this was this very useful algebraic observation. And then by using some, obvious facts about determinants. So you know that in a determinant you can add any linear combination. So if you add to any column a linear combination of the other columns, you don't change the value of the determinant. And that means you can if you recall how this thing looks, so I have a 1, and then let me try to get the columns and the rows right. So if I go down, so I have 1s here, and then I have x1, xn, I have x1 squared, xn squared, and then I have x1 to the n minus 1, xn to the n minus 1. Okay, so this is my determinant, and now you notice, for example, in this column here. So this column, every entry in this column is a simple polynomial of the variable xi. It's the polynomial x. But I could replace the polynomial p of x. I could replace it with, which is equal to x. I could replace it with x plus c for any constant c, just by adding c times the first column to the second column. And this does not change the value of the determinant, right? And similarly, in the second column, I could add any linear combination of the first column and the second column. which means I can replace all of these columns. I can replace the polynomial, which here in the second column is just x squared. I can replace it with any other polynomial which has the same degree and top coefficient 1. Okay? And these polynomials were called monic. So this was this trivial observation, but very, very important one from proposition 39, with which we finished last time. So if Pi is, so monic, I recall monic means that it's a polynomial whose top coefficient is equal to 1. Monic of degree I. Then this van der Monde determinant is in fact equal to write it in terms of these polynomials. Okay, so this is review from last time. So I think this is where we stopped last time. Right? So what do we want to do now? So we would like to analyze this measure. In fact, it's convenient for other applications, but also just for clarity to generalize the setup somewhat. So this is a simple, it's a product of Gaussians, and instead of taking a Gaussian measure, I will just take an arbitrary probability measure, and I can even go into the complex plane. That will have some applications if you want to study matrix models whose eigenvalues are not real. So we shall study measures of the following form. So a general measure. So a general measure on C to the n. So we always have n variables, so they're always going to be probability measures of n variables. And it's of the following form. I call this measure mu n. So mu n is going to be my measure. And it's going to have a density that I call rho n, and the density is with respect to the product measure of some chosen measure. So here for the GUE, this chosen one body measure, if you wish, is just the Gaussian, and in general I will take something that I call mu. Okay, so where mu, where mu is, let me start by saying what rho is. So mu is just going to be a probability measure, and rho is going to be this density, and I will consider densities which have precisely this form. So it's going to be a product of measures, in fact a tensor power of some nice probability measure, and the density is going to be given precisely by this van der Monde determinant squared. So rho n of x1 up to xn is 1 over some normalization, which will make this a density with respect to this product measure. And then I have I less than j. And now these are complex numbers, so I will use the modulus squared. And mu is a probability measure. On C, and I will assume it's supported on infinitely many points. You will see in a minute why all of the measures we take are usually some form of the Lebesgue measure, so clearly supported on infinitely many points. Okay, so this is the setup with which we are going to be working today, and also a bit on Thursday. Okay, so this is the general structure, and these kinds of measures play a very important role in random matrix theory. They lead to so-called determinantal point processes, which we are going to see today. So, so let me just review what this proposition 39 says. So by proposition, I just recall that this density rho n can be written as this van der Monde determinant squared. So rho n x1 xn is equal to the, well, I have the normalization factors. I will usually not talk about these normalization factors. I include them. They may change from line to line. They are just always chosen so that whatever I write here is a probability measure, a probability density. So this has to be a density. This has to be a probability measure, so I have to choose my z in such a way that the integral is 1. So this van der Monde determinant without the square was given by proposition 39, and so I can just square it. Okay, so that's my density. I can write it as a van der Monde determinant using any family of monic polynomials. So we have, this is the power and beauty of this method, is it gives us a lot of freedom in choosing these polynomials, and you will see later today there is one unique choice which is extremely convenient, and that's the right choice, and it is not at all the one that we have here. So it's not the standard basis of polynomials. It's something very different related to the measure mu. So where Pj is any Of course, I always want the degree of Pj to be equal to j. Okay, so this is what we have. Now, what can we do with this? Let me try to compute this determinant, this absolute value square of the determinant, a bit more explicitly. Now we can plug in. The precise form of the matrix, and we will use the fact that the determinant of A times B is equal to the determinant of A times the determinant of B. And it's also convenient to get rid of this monic assumption. And that's in fact not hard. So if we would like to allow polynomials which are not monic, in fact, that's sort of trivial. That just means we have to scale every polynomial by some number Cj, and the determinant is a multilinear function in the columns of your matrix. So you can just pull out these constants C, and in that way you can in fact relax this condition that the polynomials are monic. So let me define the following matrix. So I choose a Cj, which is a positive number. I define a matrix Aij, which is given by Cj minus 1. So I fix my, now I'm just doing, this is just an algebraic computation. So I fix my arguments of my probability density, and I would like to compute this right-hand side. Write it in a slightly different form. So I define my matrix Aij. So with this matrix, I can write my determinant in the following way. So this was the determinant that I had to compute. And now I would like I would like to put these C's inside as well. So I would like to multiply all of these guys by C's. So imagine I multiply this with a Cj minus 1. Well, I can pull it out. It's a multilinear function. I get the square. So with all of that, I get the following product. So this is the quantity I would like to compute. So just to repeat what I said, so using the multilinearity, so this is equal to the determinant of Cj Ej minus 1 xi it's given by the following Cj minus 1. That's what I want. And now let's write this in terms of the matrix Aij. Since in fact this is nothing but the determinant of A. Right? So this is equal to the determinant of A. The whole thing absolute value squared. And now I use the simple, but when you think about it, if you recall in linear algebra, there's a very non-trivial property of determinants that the determinant of A times the determinant of B is equal to the determinant of AB. And this is what I use here. And so what is this? This is the modulus squared. So it's the determinant of A times the determinant of, maybe I'll write this up in 2 steps. So this is the determinant of A times the determinant of A complex conjugate, which is equal to the determinant of A times the determinant of A star. And I probably want to do it in that order, yes? Because the determinant of the transpose is the same as the determinant of the original matrix. And this is the Hermitian conjugate. And now I can use this property of determinants to write this as the determinant of A times A star. And now I will give this matrix a name. I will define, in fact, if you recall the definition of A, so the first index here, the I index, really depends only on xi, depends on I through xi. And since this is A times A adjoint, then the second index of this whole matrix is also going to depend on the x's. Right? The J index is going to be hidden inside this matrix multiplication. So I will define this matrix. I will give this matrix A times A star a name. I will call it Kn. And as we saw, it's just a function of xi and xj. And so this is by definition A times A star ij. So more precisely, Kn xi xj is equal to the sum of, let's say, k. It goes from 0 to n. So now I'm performing this matrix multiplication. So you take this guy with xi, you take the same guy complex conjugate with xj, and then unfortunately maybe I should give this index name the name k to become slightly clearer. Okay, so you take this guy with xi, you take the same guy with complex conjugate and xj, and you sum over the k. And I would like to call this polynomial, this I will call q, k minus 1 of xi. So this is going to be equal to, well, maybe I'll do that in a second step. So for now, I get ck minus 1 squared pk of xi, pk of xj complex conjugate. Okay, so this is just a simple calculation using these determinants. But this is the key algebraic starting point of our calculations. I would like to summarize it as follows. So I will define this polynomial Q. Note that this whole derivation was true for any positive number C. So I will define a QK, which is equal to CK times PK, and these C's I could choose as I wish, and that means I can choose my QK to be any polynomial of degree K. The PK could be any monic polynomial of degree K, so the QK can be any polynomial I wish. So let me summarize these findings. So we find that rho n of x1 up to xn is equal to some normalization constant, as always. Now I use the letter C, because it's different from the Z from before. And this is equal to the determinant It's equal to the determinant of this matrix, where I put in the arguments xi and xj, and where kn was this guy. So kn, I can define kn, it's a function of x and y, and it was equal to the sum. K goes from 0 to n minus 1. And since I defined my Q to be precisely ck minus 1 times, now here I would probably, so I keep on going back and forth between the parameter ranges 1 and n, and 0 and n minus 1, and here I would like to write it like this. So I go from 0 to n minus 1, and then I have a ck but now I use the q's. So I have qk of x and qk of y complex conjugate. So these polynomials can be complex, right? So everything can be complex now. And this q and qk is any polynomial Okay, so this I will circle this, because this is the conclusion of our calculations, and this is the starting point. Okay. So this thing is called the kernel of this. We will see that this, in fact, we'll see very soon that this describes a so-called determinantal point process, which are ubiquitous in many areas of probability, originally from random matrices. And this is the so-called kernel of this determinantal point process. You've learned quantum mechanics, right? Do you all know what a fermion is? Have you seen fermions? Kind of. So this, if you wish, everything we are doing here is nothing but the theory of free fermions. It's exactly the same thing. The notations are somewhat different from the ones one usually uses in quantum mechanics, but the mathematics is exactly the same. So the proofs are the same, the arguments are the same. So if you wish, you may want to translate this into a quantum mechanical language. So the theory of free fermions, as you know, is the theory of Slater determinants in quantum mechanics. And here they are. So this is the notation and an approach that's more common in probability theory, but there's a one-to-one dictionary you can use to translate. I mean, these QKs would be wave functions with respect to this measure mu, and this would be a density matrix. In fact, we will see in a minute that the way one always chooses these QKs, this thing becomes a projection. And it corresponds to a quantum mechanical state, which is a density matrix, and it's a projection onto the span of n one particle wave functions, and there are these Qs. Okay, we'll see. I will say a few more words in that direction once we develop this theory a bit more. But so for our purposes, if you recall, what was our original goal? So I've erased the density for GUE, but our original goal was we had the density of a GUE, if you recall, dxn. And what we would like to understand is let's say the density of, for example, one particle or the joint density of two particles. These are called correlation functions, one or two particle correlation functions. And that means you would like to integrate out many variables. You would like to integrate out all but k of these variables. So this is a probability measure. If you have a joint probability measure of many variables, then you can start integrating out only a few of them. If you integrate out all of them, you get one. But you may want to integrate out just a few of them. And for example, if you integrate out all but two, then you will get some measure, which maybe I can denote it by pi n 2 of dx1, dx2. This is a symmetric probability measure, by the way, so it doesn't matter which one you integrate out. And this is the object that is the most studied and most important object in random matrix theory. It is the pair correlation function, and it describes the joint probability of having an eigenvalue around x1 and around x2. So this is what we are trying to understand. So in order to do that, we have to integrate out all of these variables. And if you go back to the form of this probability measure mu n, it's not an easy thing, right? Look at this formula. You have this interaction, this logarithmic interaction, and you can't, even integrating out one such variable is not easy. In principle, there are Gaussian integrals. You have polynomials. You have to integrate out with respect to Gaussian weights, and the factors in front are polynomials. So in principle, one can do that. However, if you start doing it naively, you will find yourself in an enormous mess, and even doing just one. And in fact, here you have to do n minus 2, for example, and then you have to take the limit as n tends to infinity. So you have to do this in a smart way, and this is the smart way to do it. So what we would like to do now, so that we would like to determine correlation functions. Correlation functions of rho n by integrating out variables. Okay, so that's what we will do. And there is a very nice lemma, which is the following, that tells you that if these polynomials Q have been chosen in an appropriate way, or more precisely, if this kernel Kn satisfies a simple property which essentially says that it is a projection operator. So if Kn is the operator kernel, the integral kernel of a projection operator, then integrating out variables is very easy. So that's the following result. So here is the condition. Suppose that we have the following condition. So think of k. Now I will drop the n. I mean, this kn was a very specific kernel. Now I'll just take a general function, k of x and y. And think of k being an operator acting on functions of C. On C. So imagine you take some nice function f, take some nice function, let's say continuous, compact support, and then you can define an integral operator acting on this function. Okay, so this is how you can define an integral operator associated with such a function of two variables, if the function is nice enough. It's exactly like matrix multiplication, except I would not like to take the integral with respect to Lebesgue measure. Now you should think Lebesgue measure does not exist. The only measure we have at our disposal with respect to which we can integrate is the measure mu, which has to be specified. Okay, so this is exactly like matrix multiplication. In fact, you could take mu to be counting measure on the integers 1 to n, and this would be precisely matrix multiplication. But if mu is supported on infinitely many points, it's like an infinite, it's like multiplication with an inverse matrix. And if you want this kxy are the entries of the matrix, and k is the associated linear operator. So if k had the following condition, what I'm going to write is k squared is equal to k as an operator. So in other words, if k is a projection, this is by definition what it means for an operator to be a projection. So more explicitly, so if x, k of x, y, k of y, z, I integrate over y, if this is equal to k of x, z, so let me give this thing a name. So this is the equation star. So this means that k is a projection. It is the kernel, the integral kernel So let's suppose that. Then the claim is I can integrate. I can integrate this density. So if you recall, this was my density with respect to the product measure mu. And now I would like to, let's say, integrate out the xn with respect to mu. And I can do that. So then the integral of the determinant and now I integrate out the last variable. And this thing, so I can not only integrate it out, I can also figure out precisely what the coefficients are in front. So I will get n minus n, r minus n. I will tell you what r is in a minute. And I recover, and this is the beauty of this calculation, I recover exactly the same determinant of the n minus 1 first variables. Of course, this cannot depend on xn, but it depends on all the others. And so it's a kind of a closed type equation. I get exactly the same expression, except one of the variables is gone. And this r, where r is this object, which, if you want in the operator language, is the trace of k. Okay, this would be the trace of this operator whose kernel is k of x and y. Okay. So this is the claim. Is the claim clear? Is that okay? So let's prove it. I mean, the proof is once I've given you the claim, then I'm sure you can prove this. It's just you just have to do the calculation. I would like to do it with you just to make sure you see it. But there's nothing smart happening in the proof. You just have to be a bit careful when playing around with these determinants, but there's absolutely nothing smart at all. We don't use any fancy properties of determinants, we just use the definition of the determinant as a sum over all permutations. So let's do that. So I will use the following notation for the permutations. So this thing, so what's the determinant of a matrix? Is the sum of all permutations, and then you put in xi and x sigma of I. Another way of writing it is to use this totally antisymmetric symbol epsilon. Okay, do you know this symbol? Should I explain what it means? Is it clear to everyone? So, I will tell you in words what it is. It is a number that is equal to +1, 0, or -1. It is equal to +1 if these indices are an even permutation of 1 to n. It is equal to -1 if they are an odd permutation of these indices, and it's equal to 0 otherwise. Okay, so that's my determinant, and then I have k, so I have k of x1, k of xi1, and then I have k of xn, xin. Okay, this is my determinant. And now comes the only point where you have to do a bit of thinking. So you would like to integrate out the variable xn. So we have to spot it, right? We have to find where does this variable xn appear. We know it appears in precisely two places, right? It appears as the first argument of this guy here, and it appears as the second argument of one of these k's, depending on the permutation I choose. And in fact, here we have to distinguish two cases. I think it's already plain. If in is equal to n, then the xn only appears in the last term. And that's trivial. To integrate out this xn in that case is trivial, and indeed this is going to give us precisely this term r. Okay, that's what you get if you integrate out xn when it appears twice as the argument in the last term. And the other possibilities are that the xn appears as the second argument of any of these n-1 factors of k. So let's do the following thing. Let's condition on where the xn appears as the second argument. So I will do the following thing. So a bit more formally, I introduce a partition of the unity. So the second argument of the kth factor is ik, and this I just introduced this sum to tell me that if I take this term, then the n appears precisely in the kth of these factors. Okay, so in fact I split this into two pieces: the piece where k is strictly less than n, and the piece where k is equal to n. So if k is strictly less than n, then I have the following sum. As always, I have my indicator function, so that I know ik is equal to n, and then I have my totally antisymmetric symbol, epsilon. And then I have all of my factors of k, so in principle nothing changed, except I would like to now write them out carefully in full. So because this xn now, it appears at the kth factor, so let me write this out carefully. And so in the kth factor, I would have an xik, but I know that ik is equal to n. So in the kth factor, I have my xn, and then I go on. until I get to the last one, my xn, and then I have my xin. Okay, so this way I've identified explicitly where the xn is. It's in two places. It's here, and it's here. And then, of course, I have the other term when k, little k, is equal to capital N. That was the easy one. So I have, again, my sum. So in particular, this is a permutation with the fixed point, which is n, since in is equal to n, and therefore this is just going to be a permutation, sum over permutations of I should probably even write it like this. And can write it just as a permutation over the n minus 1 variables, and then I have the final one, which is k xn xn. Okay? So this was the only piece of thinking I had to do. There was not really any thinking involved. You just have to carefully write things in a way that you see where the xn appears. And now we can integrate. And why does this look good? So we have two terms. So as I said, integrating out this term is very easy. I could just integrate it like that. And integrating out this guy here, I will use my projection property. And this will give me, these two k's together will just give me a new k with the indices xk and xin. And then I can do a simple renaming of variables and I will get exactly what I wanted. So let's do this carefully. So let's integrate. So this is now equal to, using this projection property star that I just erased, it is equal to so here I'm just copying what I had, and let me also copy okay, so this nothing happens to these guys, and then the only thing that changes is these two guys that go together, and I get a k of x. So I have xk, and then I have xin, right? So I get these two terms, this term and that term. I integrate over xn. I get this, and then I can continue. So then I have, again, the guys that I did not touch. So I have an xk plus 1, xik plus 1. Okay. And this one I can already do. So this one is integrating over xn just gives me this factor r. And what remains is the determinant of the n by n submatrix. Okay, so we're almost done. We just have to recognize this first term as being the determinant of the same thing, so this guy here. And we can do that just by renaming the variables. So if in the first term I rename in, if I rename in ik, this I can for sure do. So then this would become xk ik, and in does not appear anywhere else. Okay, so if I do that, I get the following thing. So k goes from 1 to n minus 1. And then I have the sum I1, in. And then I have delta in n. And then I have epsilon. Now I have to be a bit careful. If I swap the roles of in and ik, that means I do a transposition of this. I do one transposition in this permutation, which means if I now rename them so that they are in the correct order again, I get a minus sign. And otherwise, I have exactly what I needed. So this, well, the sum over in is kind of gone, and then I have x1, xi1, k, xn minus 1, xi n minus 1, and plus r times the determinant and that's the end of the proof. Okay.
Determinant to n minus 1.
N minus 1, yes, thank you. Okay, so here you see, I mean, you can of course, the sum over in vanishes by this term, and then this is of course equal to the same thing. If you just replace, if you forget about the last index, which is anyway a fixed point of your permutation. Okay, so this factor gives you an n minus 1 with a negative sign, and that was precisely what we had in our proposition. Okay, good. So I wanted to finish this calculation, which took us slightly over time. So let's have a break now. We'll have a 15-minute break as usual. We'll resume at 19 past and see how to satisfy this condition star after the break. Okay, so let me continue now by focusing on this condition star. So we saw that this integration of integrating out these variables works beautifully, provided our kernel K has this projection property. So now the question is, how do we satisfy the projection property? And remember that Kn, so this was the sum where K, I think I wrote it K, goes from 0 to n minus 1, Qk of x, Qk of y bar. And there is a suggestive way of writing, maybe even before I write down the following result, which is basically a triviality. I would like to show you how one can see this if you just argue it sort of geometrically, just using linear algebra. So let's instead of using the kernel notation, let me write it like this. And this, I regard this as a vector. Okay, so I take the Hilbert space, which is the L2 space of, with respect to the measure d mu. And this qk is a vector in this space. Okay, it's a polynomial, so it's a nice vector in this space. So what I'm doing, and this is the dual vector. I mean, you know, this in your course on quantum mechanics, you've seen this Hilbert space duality, right? So this is if you wish, the dual vector. Or if you want, in the language of linear algebra, this would be a column vector, and this would be the row vector with the complex conjugate entries. And we want this guy to satisfy this projection condition. How can we ensure that? So this is a projection, if you recall in your class on linear algebra. This is, let's assume these guys are all linearly independent vectors. This is going to be a rank n matrix. And how do we ensure that this matrix is a projection? Or we can achieve, this is going to be a projection if these vectors are orthonormal. Right? If these vectors are orthonormal, then it's basically linear algebra that this equation holds. And of course, once you know that, I mean, the calculation is a triviality, but this is sort of the geometric intuition from, if you wish, quantum mechanics or linear algebra. So the claim is the following. So suppose that these qk's are orthonormal with, of course, with respect to mu. So everything is always with respect to mu. So what does this mean? So it means they satisfy. So what does this mean? This means that qk, ql right? That's the orthonormality. So if I write it in this language that's more commonly used in probability, okay, so I make this assumption that they are orthonormal in this L2 inner product space. Then I have this projection property. So Kn x, y, Kn, y, z, mu dy is equal to Kn x, where Kn is precisely this kernel. So where okay, and the proof is immediate. There's nothing to do. You just plug this thing in. You just plug this definition in, you integrate out, and you see that just by orthogonality this holds. It's trivial. So now we know how to satisfy this condition star, and that's the correct way. And this is sort of one instance of the very general and beautiful method of orthogonal polynomials that you can use to integrate out variables of such probability measures. And so the trick is, this is why it's called orthogonal polynomials. In order to be able to do this, you have to choose your polynomials to be orthogonal, even orthonormal, with respect to this probability measure. Okay, so the proposition, So the proof is immediate. That's an immediate argument. Okay, so let's now do this. Let's actually do what we were talking about. So let's really integrate out all but k of these variables, and this leads to these k-point correlation functions. So the strategy is use these propositions 39 up to 41 to integrate out inductively from and of course the integration is always performed with respect to the measure mu. So here is our density, and we would like to integrate out all but the k first variables from mu. And this gives rise to these k-point correlation functions, which I recall. So you had an exercise on the final problem set, which was for today, about these k-point correlation functions. So there are two definitions which are equivalent, and the equivalence you understood on this problem set. So for pragmatic purposes, I can just define the k-point correlation function up to a combinatorial factor as being precisely what you get if you integrate out all but k of these variables. So the k-point correlation function of rho n is the density. So we are always working with densities. Correlation functions are always densities. So it depends on k variables, and up to this combinatorial factor, which is n factorial over n minus k factorial. It is just the integral and remember the integrations are always performed with respect to mu. So imagine Lebesgue measure does not exist. Integration with respect to any other measure does not make any sense in this universe. We always integrate with respect to mu. All densities are with respect to mu. So this is the definition. Now you saw in the exercise that in fact these k-point correlation functions more generally and in fact more correctly are associated not with such probability densities but with point processes, with random point processes. And the random point process is just a random collection of points, or more formally a locally finite integer valued random measure. And this is something you studied a bit on the problem set, so I would just like to recall. So recall from the homework, this is from the homework, so this is precisely what was called there also the k-point correlation function. The k-point correlation function of the point process So it's a very particular point process. It's the so-called eigenvalue process. Well, if these things are eigenvalues, or it's going to be the process defined by a finite number of points, which are the xi's of the point process. So what is a point process? It's, as I said, it's a random measure. So these x's are going to be random variables, which are distributed according to this joint density. And for every realization of the x's, you build this point process, this point configuration. And in the exercise, you saw that this point process has precisely these correlation functions. And the true definition of the correlation function was, for general point processes, was a bit different, but it reduces to this one in the special case of such a point process. So where has joint law, so rho joint density rho n. Okay. So this more general point of view is actually helpful when in many contexts when you want to look at more general point processes and the general theory of such point processes, but also even for applications in these basic questions of random matrix theory. In the next semester, we will see how to compute these and show the universality of such quantities in random matrix theory. And then this point of view, so the one that you saw on the problem set, the general formulation is really the correct one, and it's much more helpful. But for now, if you want to, you can ignore this and just regard this as a definition. Okay, so the claim is the following. So let me summarize. So I take a measure, which was my Xn, which is this probability measure with density rho n. And now I take my rho n, and I probably want a, yes, I want a normalization factor. Rho n is some constant 1 over c, and then I have this van der Monde determinant. Squared in absolute value. And then I suppose that qk, this family qk, are orthogonal or orthonormal polynomials with respect to mu. Then the claim is that we have an explicit beautiful formula for this k-point correlation function for any k, namely it is the determinant where Okay. So this is the punchline of this whole algebraic section. And it's a remarkable result. I think this is an extremely remarkable calculation. It tells you that you can explicitly integrate out all but a few of these variables, and the answer you get after this huge integration is extremely simple. It's just given by a determinant of a k by k matrix. So imagine k is 2, you're interested in the pair correlations. Then this is just a determinant of a 2 by 2 matrix that you have to calculate. Super easy. So the whole problem reduces to computing this kernel and its behavior for large n. So we have reduced this very high dimensional complicated problem of interacting particles simply to computing such kernels in terms of orthogonal polynomials and analyzing its behavior for large n. So of course it's not completely trivial. We'll do the example of GUE starting on Thursday. So you have to work a bit, but it becomes basically a problem of asymptotic analysis, which is an analytic problem. It can become arbitrarily hard depending on the models you are considering. But for easy models, such as GUE, it's really not particularly hard. You just have to understand how orthogonal polynomials with respect to your chosen measure look like. For GUE, if you recall, the measure mu is a Gaussian. So we will have to analyze the orthogonal polynomials with respect to a Gaussian measure. Do you know what they are? They have a name. Yeah, they're the Hermite polynomials. So this calculation is basically just going to be then an analysis of Hermite polynomials. But before going there, let me prove this result. Yes. So let me prove this result. The proof is not hard. It's basically, I mean, you kind of see, it basically summarizes everything we've understood. We just have to do a systematic integration using the techniques we've introduced. So we know, thanks to this proposition, I think it was 41, that if these Q's are orthogonal with respect to mu, then this kernel Kn satisfies the projection property. And therefore we can integrate out using proposition 40, I think it was. We can integrate out, we can start by integrating out the last variable, this one. And then we get something that is of the form of an n by n minus 1 by n minus 1 determinant. And then we can integrate the next one and the next one and so on. So it's clear something of this form comes out. In fact, the only thing that's not completely obvious maybe is that this factor, this combinatorial factor comes out right. So this is the factor you have to choose in order for this calculation to give you the right answer. And by a nice coincidence, this is also the correct combinatorial factor in front of the correlation function of a point process. So rho n, let me write, now I have to, usually I was quite cavalier with my normalizing factors. Now I have to be a bit more precise. So this Zn is whatever it is, and I will have to track it through the proof. And so let's apply this proposition so with r is equal to n. Why is r equal to n? If you recall, r was the trace. R was the trace of this operator k in this L2 space. Now if you set x is x equal to y, here we are, x equal to y, you integrate over x with respect to the measure mu. Every one of these terms gives you a 1 by the orthonormal condition on these polynomials. And therefore this r is equal to n. we apply proposition 41, which tells us, I think that was the right label, which tells us that yes, this star condition in proposition 40 is satisfied because the polynomials are orthogonal. And so now we can just integrate. So we do the first integration using proposition 40. And if you recall, we had an r minus n plus 1. So we just get 1 times the determinant of the submatrix of the n minus 1 of the n minus 1 by n minus 1 submatrix. So that was the first step. And now we integrate the next one. Okay, so I integrate out the next one, which means I have to integrate the last one in here. And now you see it's slightly different. R, so I have to be careful now. When I apply this, then the n becomes n minus 1, but the r is still my original n. So I get, so r, I have an r, which was my n, minus, this is the dimension of the matrix, this was r, dimension of the matrix plus 1, and this is equal to 2. And then I have my 1 over z n, and then I have the same thing. And minus 2. And then you can see how it goes on, right? And then I go on integrating. So every time I integrate out one of the variables, I get such a factor, and the dimension here keeps on decreasing. So these numbers, they grow, right, like factorials. And when I've integrated out n minus k variables, I will get an n minus k factorial. And what remains is the determinant over kn. I should put in the kn's. Kn. Okay. So I'm not quite done yet. I have to figure out what this Zn is, and that's easy to find if I set k. If I integrate out all variables, rho n was the probability density. That's how the Zn is chosen. And therefore, on the right-hand side, I have to get 1. So if k is 0, I have an n factorial divided by Zn, and then I have the determinant of an empty matrix, which is by convention equal to 1. Right? Empty products are equal to 1. So from this, we deduce that Zn has to be equal to n factorial, and that's what we have. Okay. So this was the key calculation. This is the calculation that serves as the basis of all of this beautiful and very far-reaching theory of orthogonal polynomials. This is somehow the starting point. Is this okay so far? Is it clear? So this is the algebraic identity we are going to use. And now the program is clear. We have to do this for GUE. So we will find the orthogonal polynomials with respect to the correct measure mu, which was Gaussian. These are going to be Hermite polynomials. And then the problem reduces entirely to figuring out how such expressions of Hermite polynomials behave for large n. And you have to do some algebra. Basically, if you understand Hermite polynomials well, it's not very hard. You have to do some slight saddle point analysis and so on. We'll see how this goes on Thursday. Maybe it would be convenient to, so instead of starting this section on Hermite polynomials, which I would not like to break like that, I could give you the interpretation of all of this in terms of quantum mechanics and free fermions. I mean, that's what I sort of talked about, and it's really just to give you an impression. It's exactly the same thing, just in a different language. So this is quantum mechanics of free fermions. So we take the Hilbert space. So now you know very well how quantum mechanics is formulated. You take the Hilbert space of your space d mu. Okay, so quantum mechanics is formulated on the Hilbert space, and you will choose orthogonal wave functions. So wave functions Q0, Q1, Q2. And so this is an orthonormal basis. And now if you would like, so what we would like to do is to consider free fermions in the state defined by the n first wave functions. Okay, so free fermions in so you know that. So what is it? What is a fermion? If I want to write down the wave function, I want to write down the wave function psi. If I had bosons, I could try to put them all in the ground state. Let's say this is the ground state. Of course, for fermions, this is not possible, right? Because this thing has to be antisymmetric. So I have to antisymmetrize this in the arguments. And if I take always the same function, then I get 0. Free fermions in state Q0, Qn minus 1. And this is going to be, so I will take Q So this is my wave function, and I want to antisymmetrize this. So this is how you antisymmetrize any function. And this is just a Slater determinant. This is the Slater determinant. Have you seen the Slater determinant in a course on quantum mechanics? Is this familiar? No, it's not. Anyway, but this is what it is, right? If you take free bosons is somehow an easier theory of free fermions is you take, why is it called free? They're called free. If you recall, in quantum mechanics, particles are free if the state factorizes as a product over the different particles. And this is the closest you can get to as a product. You can't just take the product because the wave function has to be antisymmetric in these arguments. You take a product and you antisymmetrize it, and that's, by definition, the theory of free fermions. Now, how would one get to correlation functions? What are correlation functions in quantum mechanics? How do you integrate out variables in quantum mechanics? Well, it's a bit more subtle. And maybe I would like to introduce a normalization. If I want this guy to be L2 normalized, I should probably put in such a normalization. If these guys are orthonormal matrices, then this is an L2 normalized wave function. Now, the state Have you seen this in a course on quantum mechanics? It's a density matrix. So let me call it rho n. Maybe I should not use the same terminology. Let me call it gamma n. So what does it mean for this thing to be a density matrix? It's an operator, so it's a self-adjoint operator. So it's a self-adjoint operator on this Hilbert space. It's a positive operator, so all of its spectrum lies entirely in the positive, on the positive real axis. And its trace is equal to 1. If you take a quantum system, which is in a specific state defined by a wave function, then this corresponds to a very specific density matrix, which is the rank 1 projection onto this. Which is precisely this rank 1 projection onto a vector. Okay, so you have a vector, this psi, you should view this, okay, maybe I should have given this guy a name n, psi n. So this psi n is it's a normalized vector in the antisymmetric nth tensor power of this Hilbert space. And I use this notation, so in the physics literature, people would use this notation, right? This bracket notation, which you might be familiar with. I'm not particularly fond of it. I think it's just a stupid notation, but many people use it. So it doesn't have any advantage. In fact, it disguises many important features. You just introduce lots of new symbols for no particularly good reason. But this is very popular, so that's what people, right? So this is a rank 1, right? This is just a rank 1 projection in this n-particle Hilbert space, and a rank 1 projection onto the subspace band by this one-dimensional vector, this one. This is a rank 1 orthogonal rank 1 orthogonal projection. Okay. Then how does one find, what is the analog of these correlation functions which amount to integrating out variables. In quantum mechanics, that's called the partial trace. So, so the K body, they're called reduced which I will call, I will use this notation. So this is a density matrix. Sorry, here, this of course was not correct. This is okay. So I'm working on n particle space. Is this symbol clear? It's the nth exterior power. So this is going to be the projection. So it's going to be the orthogonal projections so you take the nth tensor power of h, and then you take the projection onto those functions which are antisymmetric under exchange of their arguments. Okay, it's the usual exterior, nth exterior power. So this is a density matrix. So the claim is exactly like for probability measures. If you have a density matrix on this n particle space, then you can basically integrate out particles to get density matrices on k particle space. So there's a symbolic notation. So it's the partial trace over the particles k plus 1 up to n. And if you haven't seen partial traces, I mean, there are infinitely abstract ways of defining that using some universal properties and commutative diagrams. I think it's perhaps a bit clearer just to work in terms of operator kernels. So explicitly. So then it looks exactly like the correlation functions of probability measures. So explicitly, has kernel. So let's do this carefully. So I claim, first of all, it's a density matrix on this space. So this space consists of wave functions of k variables. So if I take a kernel, I need two sets of such variables, right? That's what the kernel is going to be. And this is nothing but the integral. I need more space. You will see it's very analogous to this correlation function we had for probability measures. You have to integrate out so mu, let me call it u, k plus 1, du n, and then I have gamma n. Now I take the kernel of the original matrix, x1, xk, u1, uk plus 1, un, and then I have y1, yk, uk plus 1, un. Okay, so you put the k first arguments to be the x's and the y's, and the subsequent ones you set them to be the same, and you integrate over them. So it's as if you were taking the trace, then you would set all of these arguments to be the same, and you would integrate over all of them. And this is just a partial trace. You can check. This is not hard to check that this is indeed a positive matrix. It still has trace 1, right? If you set all the x's to be equal to the y's, and you integrate, then you clearly just get the trace of gamma n. Okay, and so then and this is, you can work this out as an exercise. So this is all of these algebraic facts that we were discussing reformulated in terms of free fermions, which has a nice maybe physical interpretation. Then gamma n1 so this gamma n1, which is the reduced one-point density matrix, is a projection, and it is precisely given. So we know it has trace 1. This is a very nice density matrix. It's not rank 1, it's a rank n projection onto the n first states which were involved in the Slater determinant. And moreover, you can so this, let me call this, this is equal to 1 over n times kn. This is precisely the same kn that we had in our theory. And you can compute any of the other reduced density matrices as taking exterior powers of this. So gamma n kth power. Now I think I may need, it depends a bit on how you normalize this wedge operation, right? So this is, what is this? This is just the nth, this is the nth tensor power, and then you restrict it to this subspace of antisymmetric tensors. Okay, so there might be some combinatorial factors which depend on how you choose this normalization here, but I will choose the normalization in such a way that these factors are built into this guy. So this is a very beautiful fact about free fermions, and so if you wish, you can prove this. It's not hard to prove. The proof is basically you just have to recognize that what we did can be rewritten in this form, and this has the quantum mechanical interpretation. And in particular, if you take the kernel of this guy and you set the arguments to be all equal, the x is equal to the y's, then you recover exactly what we were doing up to here. Okay, so this is as some background. We will not use this, of course, in our random matrix theory arguments, but this I think is a nice thing to make a link, because people always say that these kinds of point processes are free fermions, and this is really what this means. Okay, so let's stop here, and we will continue on Thursday with the analysis of the GUE.